All right, welcome back. So today we're going to go beyond just, building a machine learning model. We're talking about building a great one, something that's truly robust, totally reliable, and actually ready for the real world. Let's dive right in.
So picture this. You've built a model, and the accuracy score, it's a beautiful 99%. I mean, you're on top of the world, ready to deploy it, and then, boom, it just fails spectacularly the second it sees new data. What on earth went wrong? This is probably one of the most common, and let's be honest, frustrating problems in machine learning. And today, we're going to get to the bottom of it.
Well, the culprit is often this sneaky little villain we call overfitting. And the best way to think about it is like this. Imagine a student who just memorizes the answers for one specific practice test. I mean, they'll ace that test for sure. But the moment you give them a new set of questions, even on the same topic, they're completely lost. That's exactly what your model did. It didn't learn, it memorized. It memorized all the noise and all the weird little quirks in your training data instead of learning the actual useful patterns underneath.
So to build models that actually work, we've got to understand this overfitting trap. We need to figure out how to tell the difference between a model that's just a good memorizer and one that's a genuine learner.
And this comparison here just perfectly illustrates the problem. Look at that jagged red line on the left. That's overfitting. The model is trying so hard to hit every single data point that it ends up memorizing the noise, not the real trend. Now that smooth green line on the right, that's a much better fit. That's what we're aiming for. A model that captures the general pattern, the signal, without getting all distracted by every little random blip.
Okay, so how do we get an honest assessment of our model's performance? Well, this is where we bring in the hero of our story, K-fold cross-validation. This technique is specifically designed to give us a much more reliable and statistically sound idea of how our model is actually going to perform out there in the wild.
Because you see, just splitting your data one time into a training set and a testing set, it can be really misleading, especially if you don't have a massive data set. I mean, you might just get lucky with your split or unlucky, and that leads to a score that's way too optimistic or way too pessimistic. That one single score, it just isn't a reliable estimate of what your model can truly do.
And this process here shows exactly how we fix that problem. With K-fold, what we do is we split our data into, let's say, 10 different sections or folds. Then we train the model on 9 of those folds and we test it on that one last fold we held out. And then we just repeat that process 10 times, each time using a different fold as the test set. By the time we're done, every single data point has been used for testing exactly once. All we have to do then is average those 10 scores, and what we get is a much more robust estimate of performance.
So the obvious question is, what number should you pick for K? And while it can vary, the most common and honestly empirically proven choice is 10. It's just been shown again and again to provide this great balance between getting a really reliable estimate and not being too crazy computationally. It's the go-to standard for a very good reason.
Okay, so K-fold cross-validation gave us an honest score. We now know how well our model is really doing. The next logical question is, well, how do we make it even better? And that, my friends, is where model tuning comes in.
This quote just perfectly captures the whole idea of tuning. It's kind of an art, but it's also a science. We're on this search for that perfect balance, that sweet spot of model complexity we were talking about earlier. We want a model that learns the signal, but doesn't get caught up memorizing the noise.
Now, before we start turning knobs and pulling levers, we have to talk about something really important. The cardinal sin of model building, data leakage. This is when information from your test set accidentally, or not so accidentally, leaks into your training process. And when that happens, it completely invalidates your results. Why? Because your model has basically cheated. It's seen the answers to the test ahead of time. So to prevent this, you have to follow this procedure religiously. Step 1, split your data. Then, and this is the crucial part, any data prep steps, like handling missing values or scaling your features, they must be learned only from the training data. You then take that exact same learned transformation and apply it to your test data. This is the only way to ensure your test set remains a truly unseen, honest piece of data.
All right. Now that we're validating our models correctly and we're totally avoiding data leakage, we can finally unleash the most powerful tool for improving performance, the hyperparameter search.
So, what's the difference? Well, model parameters are things the model learns from the data itself. Think of the slope of a line in a simple regression. The model figures that out on its own. Hyperparameters, on the other hand, are the settings that you, the data scientist, choose before you even start training. For example, you might decide how complex a decision tree is allowed to get.
These are the settings that control the overall behavior of the learning algorithm. You know, I absolutely love this analogy. Think of yourself as a sound engineer at a giant mixing board. The song, that's your data, and the model, that's your set of speakers. The hyperparameters, those are all the knobs and sliders you get to play with. The treble, the bass, the reverb, all to get the absolute best sound possible. We're not changing the song itself, we're just changing how we process it.
So the big question is, how do we find the absolute best combination of settings for all those knobs? Well, there are two main strategies we're going to compare: grid search versus random search.
This visualization is just fantastic for explaining this. Over on the left, you've got grid search. It's what you'd call a brute force method. It systematically checks every single combination from a list of values you give it. Now, on the right, you've got random search. It doesn't check everything. Instead, it intelligently samples random combinations from a range of possibilities.
Okay, let's break this down a bit. Grid search CV is exhaustive, which means it's pretty slow. It's great if you only have a small number of hyperparameters you want to test. Randomized search CV, on the other hand, is way faster because it only samples a fixed number of combinations. This makes it absolutely ideal for when you have a really large search space, especially when your hyperparameters aren't just a few categories, but could be any number along a continuous range.
Now, here's the really surprising part. You'd think being exhaustive, checking everything, is always better, right? Well, a groundbreaking paper back in 2012 by Bergstra and Bengio showed that's often not true at all. See, the crucial insight is this: not all hyperparameters are equally important. And random search works so well because it doesn't waste all its time meticulously testing those unimportant parameters over and over. Instead, it has a much higher chance of finding just the right value for the few parameters that actually matter.
And so there you have it. By moving beyond just a simple accuracy score, by using robust techniques like K-fold cross-validation, preventing data leakage, and then intelligently tuning your hyperparameters, you're not just building a model anymore. You're building a model that you can actually trust to perform out there in the real world.
But, you know, building a robust model, that's really only part of the story. What happens when your data is highly imbalanced? I mean, imagine a fraud detection model where 99% of all transactions are totally legit. A model could just predict not fraud every single time and still get 99% accuracy. It's robust, sure, but is it useful? Heck no. And this raises the next critical question. How do you build a model that's not just robust, but also fair and actually effective when your data is imbalanced? Now that is a challenge we'll be exploring next time.